or anyone who has comments or ideas how to reconcile this apparently dissimilar results or move forward. If not, I have a question for Thomas. I mean, as you said at the beginning, the spirit of all these cluster methods is to not to do an isolated system, but to look at certain boundary conditions. Now, do you have some idea what the DCA is doing and whether other cluster methods would provide different boundary conditions? Do you have some idea if the finer size people would like to mimic what you have, what type of boundary conditions they should apply?
Very good question. So, it's all speculation at this point. But you know, DCA, of course, if you think about the cluster and build space, you get something where every site in your cluster is coupled to a machine. I think that really has a frustrating effect on the striking. So then you can ask, okay, what if you did a cellular BMFT with open boundary conditions? So in that case, the beam field only couples to the surface. Would you stabilize the striking mechanism? It's something we're currently doing. So we looked at just the finite size cluster, just like DMRG with open boundary conditions on the long end, periodic percent. That also, of course, there we also get magnetic strike with finite temperature. But I thought it might be more robust. It's not. So I'm not sure once we switch on the mean field whether that survives.
But just to be clear, I mean, the type of mean field is there to mimic the infinite system. Right. The DCA has periodic boundary conditions in both directions.
Yes,
on the cluster. So that's a key difference with the open boundary condition.
Oh, absolutely. And so that's the idea of running cluster with open boundary conditions. So that's it's quite a demanding calculation.
I guess one of the things to point out is if you can't fit the stripe into that cluster that you're using, of course, cluster.
Yeah, so you have to look at a very large cluster. I think it's fair to say most helium defects are down on small.
And that finish that as also looked at the cases where the size of the cluster is not commensurate with the
Can you speak a little bit louder?
I'm just saying that another approach was done by Seneschal is clusters that are not commensurate with the periodicity of the stripe, and to do sort of cluster perturbation theory within the supercluster. So that's a way to allow look at long period things as small clusters.
So you can even do a DMFT. Yeah.
That's right.
Each side has its own.
Yeah, exactly.
You can get spikes in that case. I would say it's not quite at the same level. Sure.
Can you speak a little bit louder?
If you go to the view of a open calculation and you take typical two-phase energy units for it, and you look at your ground state energy difference against the various solutions that you find, the difference between AFP and CP. How far are you away in Kelvin? Imagine in our units, let's say, so how many Kelvins is the key? 3,000 is okay. And then like these energies, you know, the one plot where we kind of compared where the final difference between the energies, so it was 10 to the minus 3 units of T.
So that's if you can. So we are discussing energy differences between superconducting and stripe solutions without you get. Yeah, I understand. Which also means that obviously he additional very tiny calculation the model can stabilize one phase or the other.
Actually, I think the question on a little bit collaboration paper a couple of years ago where they compared the various ground states energy, ground state energy, where the difference between the width, the period force flight and all the others, which were more or less the same, was 0.01. So there would be talk about, say, 30-40. The difference between the various stripes 5 to 8, that was certainly in order of magnitude smaller than there we would be looking at the 3 to 4 Kelvin, but all these scales are very small.
I think with the 30 Kelvin, we picked up the more similar.
Yeah.
The numbers that I have was somewhat milder cases where you independent. That means now that most of the controllers orders of magnitude below their perhaps a really general question. Could it be that the different methods are trapped all together in the same error or same wrong thing? Or how do you decide what is something a complementary enough?
That's of course the ugly assumption behind everything. That's sort of like one thing that's not going to happen with very different methods somehow falling into the same trap. But because this could potentially happen when you're all code. But I don't believe that.
But there's no real scientific reason to believe that.
Yeah.
These methods are doing very, very, very different things.
Yeah. I mean, this is exactly the point. I mean, I don't believe that, whatever that means. But the point is, of course, these methods are so extremely different in their strengths and weaknesses and what they fall for. Some of them are exactly the usual zero limit, others are exactly the usual infinity limit, have systematically totally different errors. It would be highly surprising if that happens.
Are there any limits in which they're guaranteed to occur?
Well, what do you mean by conversion? All the methods are functioning perfectly. I mean, this they have these limits, but they are all different. Like for example, let's take the PMC. This becomes exact, and the limit goes to 0. Because that's sort of like the coupling of the action U doesn't matter anymore. So your sampling doesn't matter anymore. The result will be exact, just as an example.
I guess the question I was asking is maybe weird and not useful. But what I'm wondering about is that, sure, each method has its limit where it's right. But I'm wondering if there's a place in parameter space where they're all the same but wrong. Maybe not where we care about, but I don't know. I would be curious if such a
That
point
would be
in
going
space.
back to the first to the
A little bit different from the small cluster methods that there are exact as cluster limits. Also exact for U equals 0. In fact, for very small U, they tend to be not good because coherence length, for example, tends to be very long. Small U. So in fact, they become better for larger U if they get away with smaller clusters.
It's probably an issue that critics argue there must be some point in some parameter space where all these methods fail, but they have all been developed for a particular kind of problem, namely dealing with correlated electrons. But then sort of like this is what we are doing is guide for all sorts of physical insights about entanglement and so on. For example, like in DMRG and other methods, other insights. And sort of like I think we should keep that in mind that we ultimately want to solve real physical problems which give us real intuition and which these methods try to incorporate.
I think we should make this discussion a tiny bit more precise. I'm not sure I understood the question exactly. I mean, the methods we are talking about are all controlled if one can reach some limit where convergence can be established.
Yes.
So what Thomas described, all these cluster methods and embedding methods are controlled and go to the right solution if we can do it really large. Right? In the MRG would
Same.
become exact.
All
You can
exact
do your very, very crazily large bond dimensions and extrapolate to large clusters, right? Now, the question is that for each of these methods, there is a sweet region in parameter space where these extrapolations can be done, and others where it can't be done with current technology. And the great efforts that you guys have been describing is find some parameter space where this extrapolation can be done for at least two methods.
Well, I mean, the point is, you could say you have to be able to advance all these various methods, not just the two I talked about, to a point where this sweet region is now large enough that they start
That's right.
to overlap.
And so we've seen another example of this in Michel Stoke, where he showed that in that region of parameter of Q and temperature and so on, and doping, the extrapolated large cluster DCA and the completely different diagrammatic Monte Carlo method converge to the same measure. So I'm not completely sure how you phrase your question in that description. I mean, all these methods are controlled.
What I have in mind, sort of, is there are certain hyperparameters that distinguish these various ways of structuring a calculation, structuring a calculation in a series which is supposed to converge to the right result. So, for instance, this really what is motivated here is I know about DMFT, and I've heard about DMFT, and I feel like these different embedding methods there should be some continuum between. But this is not a good question for this format.
Yeah, my question is more for Uli. So I come from the frustrated magnetism community where we have similar issues. People are debating over all sorts of with very, very small energy scale. And could it be that these sort of systems are very close to some sort of critical point? Of course, I'm biased because have made some progress in magnetism, frustrated magnetism. But in the Hubbard model context, do you think that these systems are sitting near some critical point, and that's why there are all these competing states that are very close by in energy?
But it's a critical point or not. There is one, but they have often these theories which see a critical point somewhere below the superconducting goal, and others say no. The old timers, the IPC business, we can say certainly much more about it. Obviously, it's the competition in those spaces.
But the question is, if you put like T prime or something, is the convergence much faster than if you do not put the T prime? Like, it's just the Hubbard model without the T prime, without T2. It's much harder to converge than something where you clearly break or very clearly go away from.
Yeah, in the DMRG can make such a point that it feels like it converges better, but like my point is not so much the convergence to the point that I mentioned, but the convergence to the state. But there, of course, depends much more on what you choose as the initial state, because this can really kind of kill your entire calculation. But what I found very interesting is what Philippe shows in his ITEPS paper, where he sees that you take the T prime away from zero, that actually the difference in energy between the various strike phases, which I actually showed in the talk, is much larger than at the T prime equals 0 point, but it also is really close in energy, which to me is actually the clearest picture I know that T prime equals 0 case might actually be the harder one.
Maybe I can make one comment on that. The T prime equals 0 case was also the case, if you remember the normal state tools, where the strong coupling effects about reshaping the thermal surface are by far the strongest. So to a large extent, T prime equals 0 is, in my opinion, a stronger coupling power.
That reminds me, because we're talking about frustrating magnetism in the Kagome model, and the pure isotropic Kagome is probably also the hardest to face that, right?
As soon as you put some J2, you clearly
can make it more simple.
I have a question for Uli, again, to try to reconcile these different points of view. What's the perspective of doing finite temperature calculations and computing the pair susceptibility with your method? Because that would give a better handshake with cluster methods, which come from the high temperature side.
I mean, definitely there are these finite temperature methods.
Yeah, there are, but
And I
what's the
mean,
perspective of
hear
doing?
about that. I mean, there's stuff like most of
I think Alex should say
Alex
something
will
about
talk about that. The question is just of like which temperature regimes can you actually reasonably reach, which system sizes can you reasonably reach, and then ultimately that boils down to a question of good ideas, but for the powered algorithms, then sort of like with a big hammer. But this is definitely getting within reach.
Alex, do you want to elaborate further on this?
The systems are like similar to the DMRG systems, but the finite temperatures are a bit harder to do. So I think we're stuck with the 4 cylinders. And also for the Hubbard model, if you do doping, it's very hard to get like 1/8 of large stuff. But it also depends like what quantity you look at. So if you want to measure this exponential decay, it's very tough. No? But if you want to look at a simple quantity, you can get it. And actually, so the temperature range is not a problem. So you can get to very low temperature. That's kind of that's a problem. So there's like a couple of algorithmic novelties in time evolution of MPS that rather.
So is it fair to say that there is a hope in the very near future to see a convergence between all these different methods, custom methods, and METs for the normal stuff? You know, at some finite temperature, let's say roughly of the other end of the
The nice thing about these methods is actually that the entanglement gets a bit lower at higher temperatures. So
yeah,
you also need to simulate like a normal marker strength.
All these methods that we were discussing are finite size with in one direction, right? Yeah. Then I find here, I mean, if one does finite size cluster calculations at higher temperatures, and when you cool down, you reach a temperature where things break down because some characteristic length becomes longer. Now here you are to start at 0, so there is a characteristic length that is infinite. There might be a conception, even if you get convergence, that's
this is exactly the point why sort of like this emerging results on the width 4 or 6 cylinder as such don't interest me. Because they exactly are played by the problem you're mentioning. If there's a landscape which is larger, then effectively you are looking at a 1D system and spending all the effort on that. But the point is here to be kind of to basically control another method which can overcome this problem, but where the criticism is that what they do is in some sense uncontrolled. It's a typical comment you get on AFQMC and the CP AFQMC. Well, but as we all know, I'm quoting, as we all know, this is a highly uncontrolled method. I don't want to comment on that, but this is exactly what we try to answer. Is what they are currently doing with their iterations, is this now controlled enough that it's good? So like what we can do with the 4 and 6 cylinders is by the zero ratio of the little one is it's very good what they are doing. And of course, plus that it's not getting worse when they go into larger systems. But this is exactly the point is very well.
I mean, the point is that you're at 0 temperature, so there is infinite.
I don't agree with this. I mean, the correlation length is not the same as talking about the mean field. If you look at the BCS superconductor, the correlation length is small at 0 temperature. The correlation length is the difference between the 2-point function and the product of 1-point function.
I mean, way inside another thing, correlation length is small.
I didn't have necessarily correlation length for conductivity in mind, but some characteristic length. For instance, there is no participation as transport as soon as you can finite size of the system, at least in one direction. And there could be some influence of that because here you have really you are 0 temperature, so this you have transport that goes around the system. And this, the fact that you are at 0 temperature is concerning if you are start thinking about systems from high temperatures and on finite clusters, and then you do encounter temperature where the things break down. Now, if you are to start with the finite temperatures, and as long as you take all the methods that do have some finite dimensions, in that way you can't be convinced that you have the right. But even you get convergence, but this can be one. I mean, they are stuck in the wrong place. They are stuck. They could be stuck for that.
Okay. So I think that we sort of reached the end of the session because it's beyond 7:30. Let's thank again the speakers and the audience.